Hi everybody, this is Mrs. Ellsworth. Today we're going to be talking about work and power. Simple machines will be for another time. But what exactly is work? So let's go ahead and get started on this. Work is not the same thing as what it is when we're talking about going to work, or if we're going to go work on our homework, or if we're going to go work on our car. It's not the same exact thing. Okay, this is a product of how much force you apply and how far it moves. If it doesn't move, it's got zero distance, so it won't have any work. So it is definitely different in terms of physics versus what people think is work when they're going to go and perform some work on like a job. So like when you're looking at this young lady here, she is going to hold this barbell up here, but prior to that she is going to be exerting quite a big force as she's moving it upwards. So whatever that distance is, we'll count that as the distance, and then the force that she applies to it, quite a bit of force. Now right here she's just hanging on to it, but it's not moving. So if she's going to pose like this for a little bit, that time period that she's posing with that barbell way up there, she's applying a heck of a force, but she's not moving at a distance, so it wouldn't be any work done while she's holding it up there. But of course, as she's raising it up, that distance, that would become work. So let's go ahead and look at our units. Okay, force is always measured in newtons, capital N, and distance is always measured in meters. If they're giving you kilometers, then you're going to have to go and convert it to meters. So what do our work units look like? Well, in the formula is newtons times meters, Newton meters. Okay, it's got to have that time symbol in there, capital N for Newton, lowercase m for meters, okay, or a new unit called joules. Okay, and joules is named after scientist James Joule, and so we will just show these with a capital J. How else could we manipulate these formulas? Well, force equals work divided by distance, and distance equals work divided by force. So those are the two other manipulations of this formula right here. Okay, and then moving on. Okay, so here's some pictures that I have of when we're considering work being done. So if you're looking at this guy right here, while the barbells are down there, he's applying a force to it, but as long as he can't lift it anywhere, go that distance, again, remember, we've got to go a distance. Anyways, as long as he is applying that force and it's not moving, then it is not technically work according to physics. Okay, now as it's moving up, now we've got work happening. Okay, so as long as it's moving in the direction that force is being applied, that's big. Has to be moving in the same direction that the force is being applied. Okay, then it is work. Now right here, like I said, when they're holding it up there for those couple of seconds that they're holding it up there, that right there is not work because technically there is no distance being done. Now, look at this person right here walking up this, just walking across the floor. Okay, if they're walking across the floor and they're carrying these books, how much work is being done on those books? Well, nothing, because the force that you're applying to this is going upwards. Okay, and so the only time that you can count that is when you're lifting up those papers or books. Okay, now this is different because you're going over and you're also going up. Okay, and so now you can count that as being a force being on those papers because you are going upwards. Okay, because these are vectors and we're talking about the distance or the displacement in work. Now here's a suitcase that if you're going to go and pull on it this way, oh, that's not very good horizontal, or upwards, okay, then you can count this when your force vector that you're adding them up, okay, when you're counting them up and you're slightly going upwards, then you can count it. But now let's say we're strolling it across the floor. That's where most of your force is being applied. So that would, of course, count as your distance too. Now this one, where it can only count work when it's going upwards. Boy, those are some crooked arrows. Okay, so when you're lifting the bag straight up, that's a different story. That is pure work. Okay, so what is power? Power is the rate at which work is done, okay, during a time period. Okay, and so that's really good for us to even see what the formula is. It's work that you're doing during a time period. Okay, work during a time period. So what are the units we're talking about here? Joules, of course, or else Newton meters over seconds. And power then would be joules per second, or we've got another new unit, which is watts. Watts is designated with a capital W. Now we run into some problems because we've got a capital W for watts, we've got a capital W for work. One is for units, the other one is for a variable. So you've got to be careful, and students will confuse that. So make sure that you're thinking about what's going on. Okay, here are two different ways of manipulating the same formula. Oh, look it, we got another work formula. Remember, we also had work equals distance, force times distance. It also equals power times time, because when I manipulated this formula around to solve for work, I got this formula. Okay, also time equals work divided by power. Okay, so make sure you get those two formulas written down in your notes. Okay, so let's go ahead and practice some of this. Okay, you exert a vertical force, that's good, vertical means up and down, of 72 newtons to lift a box a height of 72 meters. Okay, and you do that all in 2 seconds. Well, we don't need the 2 seconds for work, but we definitely need it for power later on. So how would we solve this problem? First of all, let's write out our formula. Okay, work equals force times distance. Now, okay, the force is going to be 72 newtons. The distance is going to be 72 meters. So we'll go ahead and multiply those two together, because like our formula tells us to, and we get 5,184 joules. Okay, so that helps us figure out work. Now power, we got to use that information because we have to take work divided by time, right? So what's our time in that formula? It is 2 seconds. Okay, and so we'll take our work, we'll divide it by the seconds, and we will get 2,592 watts. Okay, watts or Newton meters per second, or else joules per second also. But watts is just a way to abbreviate it, a shorter, smaller symbol. Okay, so let's go ahead and look at our pink worksheet. So everybody get that out, and let's look at some problems. So pause and then get that out. Okay, so here, here in number 2, I just want you to think about it. I mean, we've got other ones as kilograms too. Anyway, so we've got a 5 kilogram rock that is being lifted 2 meters in 5 seconds. Okay, so that 5 kilograms is really just mass. In our formula, if you'll notice, it doesn't have mass anywhere in it. It's got force though, and we can find force by taking our mass and multiplying it times 9.8, and then we can get the newtons, if you remember that weight formula that we had from last unit. So in this case right here, that 5 kilogram rock is really 49 newtons for weight, and so we'll go put that in place of our force, and then we'll take it times the distance of 2 meters, and then we'll get 98 joules of work lifting that rock 2 meters. Now, how much power is being used? If you remember right, power equals work divided by time, and we just figured out the work right here at 98 joules. So we'll take that, we'll divide it by the 5 seconds that we got for the time, okay, and we get 19.6 watts. So if you were somebody who just worked ahead here and did 1 times 1, thinking, gee, you know, that's just such a simple problem, you've got to prepare this, because that is mass, and work does not have mass in the formula. It's got force. So make sure you prep your kilograms by multiplying it times 9.8. Let's look at another problem. Okay, I'm not going to do this one all the way, but let's look at this. A teacher pushes a 10 kilogram desk, that's not very heavy, it's pretty light, across the floor. That means it's horizontal, and for a distance of 5 meters. Okay, she exerts a force, a horizontal force of 20 newtons. So what does this picture really look like? We want to figure out how much work is done. What do we do with this information here? Well, let's go and draw a picture of this. Okay, we've got a horizontal force on this desk being pushed horizontally. We're moving it horizontally 5 meters. Now it's got a 10 kilogram desk. You can go take that times 9.8 and figure out it's 98 newtons. But what I'm pointing at here is the definition of work is that the force must go in the direction that it's moving to be work. So you only have to deal with these two numbers here. So I'll just give you that huge hint for that problem. Okay, always make sure that you're reading the problems completely. Is it a trickster? Is it telling you, trying to get you to realize, hey, is this moving anywhere? So, and also, is the problem talking about mass versus kilograms? Always read them very carefully and figure out what you need to do. I got a couple more hints for this worksheet. Okay, how much work is done by a crane that lowers 1,000 newtons of material a distance of 150 meters? Now I just wanted to think about that for a second. If you would think about, let me get it. Okay, if you would think about what happens when it's lowering this, it is actually got an upward force, but it's lowering it down. Okay, so it's actually going to move downwards. Even though you're applying a heck of a force to it, you're still letting it down gently, and to where you've got opposing direction and force, so you're going to have a negative answer. So just be thinking about that in all these type of problems. Is it moving the direction of the force? Okay, if it's the opposite direction, that's going to be negative work. So finish that problem, just keep that in mind. Okay, let's also look at this one. Okay, we've got 4,000 joules of work that are used to raise a 300 kilogram mass, so that's mass. How high is the mass raised? So we're looking for distance. So distance equals work divided by force. And again, this is not a force. You've got to prep that by multiplying it by 9.8. Okay. There are some things here that are kind of tricky. So here's a stationary wall, so that means it doesn't move. Okay. And then number 12. Okay, we're talking about a skydiver that jumps at an altitude of 3,000 meters. What is the total work performed on the skydiver? This is the work done by gravity, because gravity is pulling it downwards, and that's the direction that the skydiver is going. So we have to say it's the work done by gravity, or else we couldn't do the problem, but just to get it to go in the same direction as the force is being applied. So they're both going down. Skydiver is going down. Gravity is pulling down. So that problem, you can do it. It's not a tricky thing. It's what's really how it should be stated. Okay, here's another one. Okay, Mrs. Arbison used to work in the classroom upstairs. I need to go and change this, but she was a lovely teacher that we had here at Parkers Prairie High School. Anyway, you were walking to Mrs. Arbison's class. You were carrying your book that weighed 20 newtons. Okay, so you've got an upward force to carry these books. Okay, you walk 45 meters down the hall. This right here is talking about just straight horizontal down the hall. Okay, and then you climb 15 meters up the stairs. Okay, now we're going up. That's the same direction as your books are being carried. Okay, and then you walk another 10 meters to her room. So that's across. So it's just to remind you that you need to worry about only when the force right here is going upwards do you have to worry about the work, because that's the direction that you're lifting. Okay, let's look at the next one, number 16. A horse performs 15,000 joules of work, okay, pulling a wagon 20 seconds. That's the time. What is the horse's power? Not as horsepower. You're going to be doing a lab where the horsepower, we will convert it into horsepower. So don't worry about that in this case. We're talking about what is that horse's power. So just use your regular formula that we've been talking about in these notes. And here's one more. Number 18, a pump drains a small pond performing 120,000 joules of work. Okay, the power rating for the pump is 1,000 watts. That's your power. How long will it take to drain the pond? So this is one that you're solving for time. So this will be the formula that you use. Time equals work divided by power. Okay, well, number 20 is extra credit, so you can do that one on your own. And it's just a two-part problem, so you'll just have to read it carefully. Okay, well, see you tomorrow.